Gibbs free energy, or Gibbs energy, has the symbol G, so we can determine a change in Gibbs energy for reaction. It's simply a more convenient way to work out whether a reaction is spontaneous or feasible. It's easier than having to consider both entropy changes of system and entropy changes of surrounding, because we can calculate the change in Gibbs energy simply from the properties of our system alone. And by system, we mean the chemical reaction that we are looking at. So all we need to know for our chemical reaction is the enthalpy change, the temperature that we're carrying this reaction out, and the entropy change of the system. Now, usually this is just given as delta S in equations, but I want to start by being really clear. This is about the entropy of the system, not the surroundings. But where did this equation come from? Who made it up? I mean, they don't just fall out of the sky. So let's go back a few steps. We know for a spontaneous reaction, and by spontaneous I mean a reaction that is feasible, according to the second law of thermodynamics, the total entropy change, so delta S total, or sometimes that's delta S universe, must be greater than 0. There must be an increase in total entropy. And we can work out the total entropy change because it's the entropy change of the surroundings plus the entropy change of the system. Now, we also know that we can calculate a value for the entropy change of the surroundings if we know the enthalpy change of the reaction, because, well, let's go back a step. So entropy change of the surroundings is equal to minus delta H over T. This is something you should be familiar with. If you're not, go back and watch the previous videos in this series, please. So to calculate the entropy change of the surroundings, we need to know the enthalpy change for our reaction, for our system. Because if we think about an exothermic reaction, that releases energy. Where does that energy go? Into the surroundings, and it will increase the entropy of the surroundings. And we also need to know the temperature. Temperature is in Kelvin, and we are always making the assumption that the temperature of our reaction is the same as the temperature of the surroundings. Okay, let's combine these two equations. So total entropy change, which of course has to be positive for a reaction to be spontaneous or feasible, is actually equal to minus delta H over T plus delta S system. Now, I am going to multiply each of the components of this equation, both sides, by minus temperature. You'll see why in a minute. Just run with this. So, multiply by minus T on the left-hand side. If I do the same on the right-hand side, times minus T, they're going to cancel out. And if I multiply this component here by minus T, we are going to have minus T delta S system. So that gives us this equation. Minus T delta S total is equal to delta H. Remember, we've got rid of the negative sign because we multiplied by negative temperature. Minus T delta S system. This looks really, really familiar. What does this look like? Well, it looks a bit like the equation that I gave you at the beginning for finding the Gibbs free energy change for reaction. Delta H minus T delta S system. So what we're saying is that minus T delta S total is the same as our Gibbs free energy. They're exactly the same thing. So delta G is equal to minus T delta S total. Or, if I turn this round, and I think it's a bit more useful if I've turned it round, delta S total is equal to minus delta G over T. Now we know that the entropy change, total entropy change for a reaction that's spontaneous must be positive, which means if these two terms are the same, that the Gibbs free energy change for a spontaneous reaction must be negative. So in summary, if our change in Gibbs free energy is negative, it is less than 0, we have a spontaneous or feasible reaction. If it equals 0, then that tells me that my reactional process is at equilibrium. So freezing point, melting point, at equilibrium point for reversible reaction, for example. And if it's positive or greater than 0, then my reaction is not feasible. It is non-spontaneous. So before we crack on to have a look at a couple of A-level calculation questions, I just want to pull this equation apart a little bit more, because as is so often the case, students are very good at taking the expression, throwing in numbers and coming out with an answer. They're not so good at explaining what that answer means. Gibbs free energy is useful because it brings together both the enthalpy component for a reaction and the entropy component for a reaction, and that depends on temperature. So where we have an exothermic reaction, we know that delta H is going to be a negative value. So an exothermic reaction favours a spontaneous or feasible reaction, because for a spontaneous or feasible reaction, we also require delta G to be negative at the end of the calculation. Similarly, because of this minus component within the equation, a positive entropy change, so a positive change in entropy, is also going to favour a spontaneous reaction. So what happens when that's not the case? Well, that is where temperature plays a very important role. At low temperatures, this component here is going to be of very little significance to the overall change in Gibbs free energy, because we are multiplying the entropy change by the temperature. So if temperature is small, this whole component is also going to be very, very small. So at low temperatures, our Gibbs free energy change depends mainly on the enthalpy change of the reaction. So if it's an endothermic reaction and delta H is positive, then assuming that the entropy change is also positive, as we heat up the reaction and the temperature increases, the significance of this minus T delta S component of the equation becomes more significant, and our reaction at some point is likely to become feasible. So endothermic reactions are feasible at high temperatures. We know that. A good example is the thermal decomposition of metal carbonates. This is one I'm sure that you know well. You take your marble chip and you heat it and you heat it and you heat it and you heat it, and eventually we get to a point where the temperature is high enough that the reaction becomes feasible. Now, at very high temperatures, the minus T delta S component of this expression is going to become significant. And at high temperatures, we find that the change in Gibbs energy is more dependent on minus T delta S than it is on the enthalpy change. It's more likely to depend on entropy than enthalpy. Now, if we have a negative entropy change, so entropy decreases during the reaction, then at low enough temperatures, our reaction still may be feasible. Why? Because as we reduce the temperature, T becomes smaller. Because we're multiplying T by the change in entropy, this whole term becomes smaller and it becomes less significant. So where we have got a decrease in entropy, the reaction still may become feasible as the temperature drops. A good example is freezing, where we go from, say, water molecules floating around, minding their own business, high entropy, to ice, a much lower entropy state. We know that if we decrease the temperature below 0 degrees C, then our ice is formed, water freezes, because the temperature is low enough that the reaction then depends on the enthalpy change, no longer on the negative entropy change. However, temperature cannot fix all ills. If I have got an endothermic reaction, so my enthalpy change is positive, and I have got a decrease in entropy. For some reasons I find that easier to get my head around with entropy than positive and negative. A decrease in entropy, so that the overall entropy change of system is negative, then in that case delta G is always going to be positive, whatever the temperature, and our reaction will not be feasible. Okay, so let's have a look at a couple of exam-style questions. So the first one, show that ice will melt even spontaneously at plus 10 degrees C, but not at minus 4, given the following information. We've got an enthalpy change and we have got an entropy change. So first things first, delta G equals delta H minus T delta S. I have got an enthalpy change. It is plus 6.01. I have a temperature. My first temperature I'm going to look at is 10 degrees C. This needs to be in Kelvin. So 10 degrees C is 283 Kelvin. So that is going to be minus 283. And that is times the change in entropy. Now, enthalpy is in kilojoules per mole. Gibbs free energy is in kilojoules per mole, but entropy is in joules per Kelvin per mole. So we need to divide that number by 1,000 before we use it. So minus 283 times 22.0 over 1,000. And when you plug that into your calculator, you get a value for minus 0.216 kilojoules per mole. And that is my answer. So ice will melt at 10 degrees C because we have a negative change in Gibbs free energy. I know it's only tiny, but it is still negative. Remember always to put the sign into your answer. The sign is really important for enthalpy, entropy, Gibbs energy changes. You need to put the sign in. What else do we need to do? But not at minus 4 degrees C. So we can repeat this calculation. Delta G equals delta H minus T delta S. You know, I'm a big fan of setting things out. So the enthalpy change has not altered. The temperature has. 4 degrees C is 269 Kelvin. So that's 269 times 22.0 over 1,000. And that plugged into your calculator should come out at plus 0.0920 kilojoules per mole. Again, the sign is really important. And you'll notice that I have given both my answers to 3 significant figures because all the information in the question was to 3 significant figures. Hence, I have put a 0 on the end there. Really important to A-level. The second type of A-level exam question involving Gibbs energy requires a little bit more thinking. To estimate the melting point of sodium chloride, giving the following information. First of all, we need to be aware that melting point is when the solid and the liquid, in this case the liquid ions, are in equilibrium, which means that delta G equals 0 for processes or reactions at equilibrium. Therefore, 0 equals delta H minus T delta S. I can rearrange this equation so that T delta S is equal to delta H. And then if I divide through by delta S, we have this equation here. Temperature equals delta H divided by delta S. Once again, quite often the textbooks just say, go learn this equation. And a lot of students have no idea where it comes from or even how this is related to Gibbs energy. It's really important you understand the underlying chemistry. Now that we have this, we can just throw in our numbers. So the melting point for sodium chloride is going to be the enthalpy change, 30.2, divided by entropy. Once again, this value here needs to be in kilojoules per mole, so I can divide by 1,000 or I can multiply by 10 to the minus 3, whichever way works for you. So that's 28.1 times 10 to the minus 3. Now we've looked at it both ways. Plug that into your calculator and it comes out to be 1075 Kelvin, which is really, really hot. And we know that this is likely to be the case because the bonds, the ionic attractions in sodium chloride are really, really strong. It's going to take a lot of energy to break up that lattice. If this has been useful, hit the subscribe button, the effortless way to support your studies. And by clicking the link in the blurb below, it will take you straight to the Crunch Chemistry School, where you'll find all the resources you need to get that A-star grade at A-level. Together we can do this.